Hey guys, I'm Matt, a developer from Ohio, and in this video, I'll be walking you through the election results project. To complete this project, you'll need to be familiar with arrays, distribution types, and matplotlib histograms. Let's get started. In this project, we use Numpy and matplotlib to examine an election survey. We'll look at how close the survey got to the real election result and find a way to make the survey more accurate. First, we need to import Numpy and matplotlib. So for Numpy, we can just import Numpy as np. For matplotlib, we only need the pyplot module. So from matplotlib, we're going to import pyplot as plt. The responses from the election survey are stored in survey responses right here. We can count how many responses are SUBIOS by using Python's built-in sum function. We'll iterate over the data and add 1 every time the response equals SUBIOS. Then we'll print out the result. So total SUBIOS is going to be sum, and we'll pass into that a list here with the following logical expression. We're going to add 1 for every response in survey responses, which is this list of responses. We're going to add 1 for that response if the response is equal to SUBIOS. So this is going to iterate over all of these submissions, and every time one of them is SUBIOS, we'll add 1 to total SUBIOS. Let's go ahead and print that out. We'll print total SUBIOS and hit save, and we can see that 33 of these submissions are votes for SUBIOS instead of for Kerrigan. To find the percentage of responses that are SUBIOS, we can divide the number of SUBIOS responses by the total number of responses. So the total length, I'm going to save as its own variable here, and that's just going to be the length of survey responses. So that's how many entries we have up here. Then we can get the percentage of votes for SUBIOS by dividing total SUBIOS up here, divide that by survey length. And then we'll go ahead and print that out. When we hit save, we should see our percentage, but instead we see 0, which we know can't be right because there are SUBIOS votes up here. Obviously, it's not 0%. So the problem is that total SUBIOS and survey length are both integers, meaning whole numbers with no decimal places. We'll get a much more accurate answer if one of our numbers is a float, which just means a number that does contain decimal places. So we can convert a number from an integer into a float by wrapping it in the float function. I'm going to go ahead and wrap our survey length in the float function. And now when we save, we've done floating point math instead of integer math, and we got a number with decimal places. And we can see that about 47% of the votes are for SUBIOS. In the real election, 54% of votes were for SUBIOS. In our survey, only 47% were for SUBIOS. This may not seem like a huge margin of error, but it's the difference between a winning vote and a losing vote. Maybe our sample size was too small. We're going to find out exactly how likely it was for us to get the wrong prediction, given our specific sample size. Later, we'll check that likelihood with a different sample size. To accomplish this, we'll generate a graph of possible outcomes for our given sample size. The data for this graph is a binomial distribution centered at 54%, which is the result of the vote. You can see on this graph that I've gone ahead and made ahead of time that our survey result, 47%, which is somewhere around here, is less likely than 54%, which is the peak, but it's definitely not impossible. To generate our binomial distribution, which is just a long list of percentages, we'll use NumPy's random.binomial function. This will have 3 parameters: the number of surveyed people, the real vote result, and the number of people who really voted. So our possible surveys is going to be np.random.binomial, and we're going to pass in survey length. We're going to pass in 0.54, which is the actual result of the vote. 54% voted for SUBIOS. And we're going to add size equals 10,000, because 10,000 is the population of the town. We're also going to divide this distribution by the number of surveys in order to scale it correctly to our sample size. So we're going to add divided by survey length. And again, what this is doing is scaling the results to our sample size here. Now that we have our distribution, which is a list of percentages, we can use matplotlib to render a graph, just like we showed on the right here. We'll render possible surveys from 0 to 1 because it's a percentage, and all percentage values are going to be between 0 and 1. So plt.hist, which is short for histogram, we'll pass in possible surveys, which is our distribution. We'll set the range to be between 0 and 1, and we're going to use 20 bins here. Then we'll use plt.show, and if you save this, you'll get a graph just like this one. Play around with the number of bins here, which is just going to be the number of columns that you get in your graph. But 20 is a good balance here. Too few, and the peak will be hard to identify. And too many, and the statistical noise will obscure the result. Back to our original question, and the reason we made this graph. How likely is it that we'd get an incorrect prediction? We can get the exact percentage by dividing the incorrect predictions, that's every result on this graph below 50%, by the total number of predictions. The total number of predictions is just the length of the possible surveys list. We're going to make this a float just like we did with the survey length in task number 3. So possible surveys length is going to be float length possible surveys. This is going to give us the float version of the length of this binomial distribution. We can use a logical condition to get the number of surveys with the incorrect result. So we'll save that as incorrect predictions, and that's going to be the length of possible surveys. And from possible surveys, we're only interested in the values that are less than 0.5. What we're doing here is getting all the values on this graph that are less than 50%, and we're getting the length of that list. Then we can divide one by the other and print out the resulting percentage. So the Ceballos loss surveys is going to be equal to incorrect predictions divided by possible surveys length, and then we can go ahead and print that out. With this sample size, we can now see that there's about a 20% chance that we get the wrong prediction. We'd definitely have less chance of failure if there was a larger sample size. So let's repeat the last few steps with a sample size of 7,000, which is 100 times bigger than the data in survey responses. So we're going to get our large survey length, and instead of getting the length of something, we're just going to go ahead and say that it's 7,000. And again, we're making this a float because we don't want to get that error with integer math that gives us just 0 instead of a percentage. Our large survey is going to be another np.random.binomial with large survey length as the length, and 0.54 as the actual result, same as before, and size is still going to be 10,000 because that's still the population of our town. And we're going to divide this by large survey length to scale it to 7,000 instead of 70. I've added a second histogram to show you the difference between a sample size of 70 and a sample size of 7,000. Notice that the large survey is much more concentrated around 54%. It's much less likely to get that 47% result that we got from the 70 survey. I've left the code for this here. You can go ahead and copy that if you want to see the graph for yourself, but that's not really a part of this lesson. Now let's get the percentage chance that our large survey makes an incorrect prediction. We're just going to repeat task 6, but with the large survey. So this time, our incorrect predictions is going to equal the length of large survey, where the large survey value is less than 0.5, because those are the incorrect predictions. And our Ceballos loss new is going to be the number of incorrect predictions over the large survey length. Then we can go ahead and print that out. And if you hit save, we can see the new percentage. You can see that there's a 0% chance to get a result below 50% when using a sample size of 7,000. This shows clearly that a larger sample size will result in more accurate predictions and less chance of failure. In this project, we used Numpy to analyze the results of a voting survey and compare sample size accuracy. We created random distributions with different sample sizes to demonstrate that a low sample size introduces inaccuracy, and we used matplotlib to represent this visually. I'm Matt for Codecademy. Happy coding!